Hi, I'm Scott Vokes, and today I'm going to talk about data compression. So data compression is very, very general, and you can plug it into a lot of other things. People tend to sort of treat it as just a magical thing that you use, but it works so well that you don't necessarily think about how it necessarily works. But if you understand a little bit about the fundamental algorithms that it uses, you can employ it much more effectively. And so you tend to see it used a lot in things like content-encoding gzip, where you can pass data through in an HTTP connection and gzip it, and then transparently that reduces the bandwidth quite a bit for any web traffic. Or likewise, on Windows, you can select a bunch of files and say, send to a compressed folder. And that way you can just pass around a single file rather than having to deal with coordinating a whole file tree or anything like that. And likewise, there's tarballs on Unix. And also, compression is very important for multimedia encoding, so that way you can do streaming audio, streaming video, and it uses only a tiny fraction of the bandwidth that it would use otherwise. And nowadays, when people design new functionality, it's worth considering what data compression can do in it and take advantage of that. And I read a good blog post where the author Kragen's attacker talked about how in the curses system on Unix, it does a lot of complicated analysis to figure out how to take the current screen and then a change that you want to make on the text console and diff that, and then actually send as little data as possible to update the screen, because if it's being used over a slow telnet connection or something like that, it could get very laggy. But his argument is that most of that effort was wasted because they could have just passed the first screen and then the new screen and then passed it through gzip and let it do that. And in a lot of cases, it would actually do that more effectively than the analysis that they try to do by hand. And similarly, I've seen a lot of programs now that like their saved file format is actually something that looks like binary data, but it's just compressed. And if you unzip it, it's either a flat text file or it's XML or something. And then that way, you get the best of both worlds because you can see all of the actual data for it in a human readable way, but you don't have to deal with the size that adds for it. But fundamentally, what is data compression? Data compression is a way to automatically detect and reduce duplication in arbitrary data. Essentially, it's a form of machine learning. It's attempting to learn about the structure of data, possibly on the fly as it's streaming in, and then restructure it so that it can be smaller somehow. You have, here's a couple strings, one of which doesn't really have any clear pattern to it, and the other has a very obvious pattern. And there's a term in information theory called Kolmogorov complexity, which represents the smallest possible way that you could describe a given bit of information. And in the case on the left, you pretty much have to pass the string through exactly as it is because there's not an obvious way to represent that in a smaller form. Whereas in the one on the right, it's just AB, 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 AB. And very obviously, you could just say, repeat AB 8 times. And that sort of description ends up being a lot smaller. There are two main flavors of compression. And I'm mostly going to talk about lossless data compression in this talk. There will be some content about lossy compression at the end, but I'm a lot more familiar with lossless compression. And for lossless compression, there's gzip and zip files, which are used a great deal. There's also GIF images and many, many other things. And there's also lossy compression, which is particularly common in multimedia data formats, like in JPEGs, MP3 files, and so on. But it's also worth noting here that GIF images tend to use a lossless compression too, and there's some reasons for that. In that case, usually it's not like photographic images that can be blurred together and such. It's more like diagrams with very crisp edges to them, and so lossless methods are very effective there. And here are a bunch of lossless algorithms that I'm going to cover, starting out with some very simple ones. So first off, there's run length coding. This is really, really easy to implement, and probably everybody has independently invented it at some point or another, including like office pets. So you have A, B, 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 C, and so on. And to do run length coding on this, to start out, you'd say A. Okay, we have an A. pass that out as is. Now we have 5 Bs, and instead of passing those through exactly as they are, put a count in there, and then a C, and then 10 Ds, and then an E. Now the other thing is, there's multiple ways of representing that sort of data. You can have most of the data be exactly as it is, and then put a special marker to indicate that something is going to have a count applied to it or something like that. Or you can put a count on everything, or represent that at like a bit and byte level in various other ways. And this is an implementation detail that isn't necessarily a part of any of the algorithms, but it's something that often matters a great deal in practice. And next, there's delta coding. So if you had a range of integers like this, typically fairly large numbers, but these are sorted, and the gaps between them are fairly small. This could be like integer primary keys from a database query or something. It's often a lot more effective to just store the base number and then represent the distances between them. And then there's ways of doing variable bit coding for numbers so that you don't have to have something take up, say, always 16 bits or something like that. There's gamma coding. There's a couple other things like that, where if on average most of your numbers will fit in 4 bits, you can shrink those down quite a bit. But that's outside the scope of this talk. And another thing with delta coding and many other compression algorithms is that this works very well when you have a sequence of numbers with small gaps between them, but every once in a while you'll have a big jump. And so you need to have a special way of encoding that you're setting a new base number that they're all relative to or something like that. It's very characteristic of data compression to have data that you're passing through and metadata about it, and they're both going out through the same channel, so you have to be very careful about how you differentiate those. And another one called Huffman coding is a little bit more complicated. But still, that dates back to the early 50s, and that's really a fundamental sort of thing. It's a way of, instead of representing data in a typical character set like ASCII or UTF-8 or something, coming up with a custom bit encoding for data that is based on the statistical properties of the data itself. And a good example of this is Morse code, which was designed for English to come up with a very short way of representing letters. And so very common letters have a really, really short representation like E or T, which are just a dot or a dash, whereas letters that are very, very infrequent in English text can have a longer pattern for them. And Morse code is not exactly the same here because Morse code is actually trinary. You can say dot, dash, or pause. Time is an element in it, and in a bit stream, that's not necessarily the case. But conceptually, it's very similar. And the way that you implement that is you take whatever data you want to compress, break it into tokens, and tokens in this case could be individual bytes. It could be all of the words that occur in a document. It could be just any sort of atomic unit, and what that is very flexible. And then you sort them by frequency. And then you pick two of the elements that have the lowest count, and then merge them into a tree that has one node above them that goes down to them. And then you keep doing this, merging together items with the lowest counts or nodes that have lower sum counts, and gradually build up an unbalanced binary tree. And I'll show a diagram for that in a moment. And this is really good because it adapts to the characteristics of your particular data. So if you have something with a typical distribution to normal English text, like the phrase "the cat in the hat" here, which has T's and E's and H's and some other fairly common letters, that might not be that different from a normal encoding. But if you have something that inverts that distribution, like the second line there, which is syzygy of zephyrs, that has a lot of Z's and Y's. And so if you tried to do that in Morse code, it wouldn't be very good. And so it can automatically adapt to that sort of thing. And likewise, humulus lupulus there, in which every other letter is a U, it can pick up on that also. So what this looks like in practice is, I've color-coded these because you might not be able to read them, but there are 3 nodes that have a count of 1, which are N, I, and C. This is for the phrase "the cat in the hat." And then there's one that has 2 for the letter A. And then there are 3 H's. And then there are 4 T's and 4 spaces, which I've represented with underscores here just to make it easier to see. So we grab the 2 nodes with lower counts, and there are actually 3 of them here. You can pick any of them. It doesn't really matter as long as you have a deterministic way of breaking ties. So you merge those, and now there's a node that has 2, and then you merge another pair that has the lowest counts, which in this case could be the other remaining 1 node and one with a count of 2. That could be either the 2 node that was just created or the letter there with a count of 2. And then you keep merging, and then you get to the point here, there's a bit of a jump where the space on the far right jumps up to the left, and then you merge 1 more time, and everything is contained in a nice little tree. And then the nice thing with this sort of tree is that if you swap the arrows in the other direction, you can also use this as a way of decoding arbitrary bit patterns to those letters. You can see the table on the upper right there. T and H and space have a coding where they're all representable in 2 bits, whereas the other letters, which are deeper down in the tree, can be represented in 4 bits. But since, on average, those occur quite a bit less frequently, the overall document will be compressed quite a bit better. And also, because this is a complete tree traversal, there's no ambiguity about which nodes you're ending up in. So you don't have to worry about breaking the data into byte boundaries and saying, I know where this is the end of one letter and the beginning of another letter. Just anytime you end up at a terminal node, you add that to the output stream and then continue. One downside with Huffman coding, though, is that this tree needs to be output with the data, so that if you have a very, very small amount of data, just including that tree itself might actually end up increasing the overall size. So there are also some more sophisticated algorithms than that, and I'm going to go next to LZ77, which is commonly referred to as sliding window compression. It's named after the 2 people who invented it, who were Jakob Ziv and Abraham Lempel in 1977. And this is called sliding window compression because it has a buffer referred to as the sliding window for recent content that is passed through it. And then as content goes through it, it either outputs data literally or it includes back references to recent things that have occurred. So that if you have something that is being put through it and then has occurred several times in the last 32 kilobytes of data or something, it can just put a back reference to that. And it can represent that in a much smaller way than putting the whole string in there again. So here's another string with some repetition in it. And stepping through this, first off, it begins with A, B, and C. Those don't appear in the buffer yet because this is the very start of the string. We haven't done anything. So those just get put out as literal characters. And then there's ABC again, but we just saw that. So instead of including that 24 bits for those 3 characters, we can just put in a back reference that says go back 3 characters and then grab the next 3 characters from that point in the stream. And that can typically be represented in, say, 11 bits, maybe 10, maybe 9 or 8, depending on how big that buffer is. And that's just a couple bits representing the offset negative into that buffer from where the output currently is, and then the length for the number of characters to pull out. So then next, we have a D, which hasn't appeared yet, so that goes out literally. And then we have ABCD, which we just saw, and so we can include a back reference to that again. And then EFGH. And then now we run into ABC, ABC, which this could be represented a couple different ways. We could include the ABC that begins this string twice, but LZ77 is greedy and will always try to take the largest match that it can, because usually from a compression standpoint, that's the best thing to do. And so it'll run all the way back to the beginning of the string and then take those 6 characters that occur there. And if that string has occurred many, many times, it doesn't really matter which of those in particular it would refer to. Typically, it will grab either the most recent occurrence or the oldest occurrence that's still in the buffer, just depending on how the implementation tends to lean, either oldest or newest, but it doesn't really matter. And then the hij at the end of that string gets put out literally because that hasn't occurred at all elsewhere. Also, since the recent output is used to store the patterns, it doesn't need to include any sort of encoding tree like the Huffman method or anything else like that. It's just the buffer that it's doing its temporary work in to do the decompression is also all of the working space it needs to store those patterns, which is a really useful property because it means you have a very fine-grained control about how much working space it needs. And also, one other example, since it's International Talk Like a Pirate Day, a back reference can also work kind of like a train that's laying down its own tracks as it's rolling along because it's going into that output buffer, not the compressed data, which means that in a string like this, it would output the A literally and then the R, and then it could say, back up one character and grab the next 9 characters. And when it's decompressing, that works perfectly fine because that output has been expanded and is available to refer to. But this is really handy because, first of all, you get run length coding for free. And second of all, if you have very sparse data, like bitmapped images or something like that, this is really effective. And so, but that's just something that falls out of the way that it's typically implemented. So the next method I'm going to talk about, LZ78, commonly called dictionary compression. This was invented by the same people the following year. And in this case, instead of having a sliding window that you're looking for repetitions in, you have a table of patterns that you're using as substitutions. And it starts out empty. And you look at the next byte of output and say, hey, have we seen that pattern before? And if so, then include a reference to it and as many of the characters following it as you can grab. Otherwise, create a new pattern starting with that byte. And then after that's gone on for a bit, you have a table of a couple short patterns, but as you make a substitution, you create a new pattern that refers back to it, and so the patterns that are useful keep growing, and so you end up with the patterns that have been most useful for this particular data set getting very long as they are still useful. And this is also a persistent data structure, although it wasn't really something that was defined in those terms back then, because the table starts with a single character, and then that's immutable, but it consts another character onto it. It's like a reversed list. And so that way, any of the ways in which that grows, it can just add on one more index and say, OK, and then continue with this other pattern. And then the other thing is that when the dictionary is too full, it just throws the whole thing out and starts over. And this is a very effective way of adapting the patterns that are being used to recent context. Most data compression algorithms try to use a property of locality because, say, in a text document, you might have a phrase that comes up a lot, and then in the next chapter of a book, you don't hear about that anymore. And so adapting to that sort of thing tends to make compression more effective. It also means that it can run in constant space because you have a buffer that you're filling up with patterns and then emptying, and you can just keep reusing that buffer. And also, this dictionary doesn't need to be transferred either because it's being built up on the fly, both on the compression and decompression sides. So many, many things that are in common use are just slight variants on LZ77 or LZ78 because in the most general case, they're really, really effective. But often they're combined with Huffman coding, or there's some other little changes to how they're implemented that make them more effective. And a good example of that is LZSS, Lempel Ziv Store Zemansky, which is based off of the sliding window technique. And this is also a pattern that you'll see a lot where there's LZ something compression, which is Lempel Ziv, and then the people who implemented some novel variant of it just tack their names on the end. So like, if you go to Wikipedia, there's a category node that says LZ 400 different variants, but most of them, you can just say, oh, is this based on dictionary compression or sliding window compression? Oh, OK, how do they vary on that? And so it's pretty easy to pick up on them. So with LZSS, In the LZ77 method, it will always take substitutions, even if it's adding a substitution that takes up more space than just including the data literally. It's greedy in that way. But the point of actually breaking even tends to be more substituting 2, maybe 3 bytes. It depends on a couple things. And also, the original method used a whole byte marker to indicate whether it was literal text or something that represented a back reference. And there's absolutely no need for that. So instead, this uses a single bit, and then it does all of the necessary bit shifting and buffering and all of that stuff. I think that Lempel and Ziv were more thinking about this from a mathematical standpoint and not really like a data structure bit packing kind of standpoint, which is perfectly fine. And then another variant is Lempel-Ziv-Welch, which is based off of the dictionary methods. The most significant difference there is that it starts with a smart default dictionary that has all individual bytes in it and a couple other patterns. And that means that since it knows from the get-go that this code represents just the letter E or the @ sign or something like that, it doesn't need to take any space for those in the table. So it's able to do a bit more patterns in the same amount of space that way, which means it can compress more effectively. And another reason that LZW is a good example is it was at the heart of a really nasty patent situation. If any of you remember the burn all GIFs thing, the GIF image format has LZW designed into it as part of the standard, but LZW was actually patented at the time, and you had to get a license to use it, which conflicted really badly with how it was becoming a very ubiquitous image file format. So among other things, the ping image file format came out of trying to design one that didn't have those sort of IP restrictions. And that patent has been expired for a while, but there's a lot of other compression methods that are patented, and I'm just not even going to bring them up because you really can't do anything with them. And another one is DEFLATE, which is used in gzip, and it was also used in pkzip on Windows, and I believe it's used in the standard zip file format for compression on Windows. And so if you use the zlib library to do data compression and you don't specify a particular algorithm, it'll default to this. It'll default to having like a 64 kilobyte hash table in memory that it uses with character trigrams, 3 consecutive characters to do dispatch to try to find patterns faster. And it has a special block header that says, for this next data passing through, do we want to use Huffman coding? Do we want to use LZSS? Or do we want to use both of them in combination, one then the other? Or some content, if it's already been compressed, like if it's video data that's been encoded some way or something, then it can also just pass that data through without doing anything to it. Because if you take a bunch of data and then you have to put 1-bit marker on every single byte saying, oh, literally this, literally this, literally this, then it just expands it by 1/8, and there's no point in doing that. And then finally, for the lossless compression, I'm going to talk about the Burrows-Wheeler transform. But so besides trying to search for repeated patterns, you can also pre-process data to make it sort better, or to make it compress better. And a particularly obvious transformation is if you sorted data, it would be a lot easier to compress well because you'd have long runs of the same characters. And there's a guy who made a version of the King James Bible that has been fully sorted letter by letter. And so there's just, can you see that okay? Okay, cool. And so there's just pages and pages of E's and stuff. And obviously, that would compress a lot better than if you were trying to work with that with all of the words in their normal order. But the problem with sorting like that is that it's a one-way process. You can't sort something and then compress it and then magically put everything else back in the original order. Now, if only there was one weird trick you could do to undo the sort. Now, there's this transformation called the Burrows-Wheeler transform, which is sort of partially sorting, but in a particular unusual way that you're able to undo. And this has the effect that if you have a lot of very localized patterns, like TH in English is a good one, you have the, you have there, you have this, that, stuff like that, it will tend to group together so that you'll get a lot of runs of T's and H's adjacent to each other, and so the output from that transformation will tend to compress more effectively. And if you've ever used, I believe it's actually called bzip2 now. The B there stands for the Burrows-Wheeler transform. That's what distinguishes that, and that's why it's often more effective at compressing certain kinds of data. So the way that this works, usually this is done in large blocks, but I'm trying to stick with what you can actually see on a slide. So I just picked the word repetition here. Now, if you add a starting marker to this, and then take all of the single character rotations of that, so you see there's repetition, and then you drop the first character and put it at the end of the line, and each line is slid over by 1 byte. Now, if you do that, and then you sort those lines lexicographically, so now the start one is still at the beginning, but all of the other lines have been rearranged. So you see it goes E, E, I, N, and then T is at the end because alphabetically that's the last line to appear there. And if you just take that last column, even in this small example, you can see that 2 of the T's wound up together because repetition is repetitive. Now, you can take that last column of that matrix and compress that, but you can also undo that transformation. And the way that you do that is if you save that last column and then sort it again, and then take that column and tack that onto the front of it in the next to last column, and then sort that, and then add the column again to it, and then just keep ticking through that, you can see the original string start to emerge there. And then you sort it one last time, and because there's a special start marker on it, you know which of those rotations is the original string, and there we go. And the other funny thing with this is the people who discovered this had no idea what to do with it. They're just like, wow, it's amazing that this works, and it never fails to amaze me that this works. But it was over 10 years before they realized, oh, this would actually be really useful for data compression. And until then, I don't know if they just like impressed people with it at parties or something like that. But also, the actual implementations of this don't use like a big matrix of characters. They use one array with a bunch of offsets in it. But conceptually, it's a lot easier to think of it as working that way. But since it might be run in like a 64 kilobyte block or something, you wouldn't want to square the size of that in memory because that would take up a dreadful amount of space. And speaking of memory, so recently I was working on an embedded project and I needed data compression for that. And before I get into that, how many of you have done any embedded work or like cool or Arduinos, stuff like that? Okay, keep your hands up. How many of you have ever run gzip on an Arduino? Yeah, exactly. Gzip assumes a minimum of 64K of memory for its hash table, and that's just completely out of the question. In a lot of embedded projects, you might have, a few kilobytes of RAM, maybe 512 bytes, depending on what kind of chip you're on. And also, a lot of embedded projects are hard real-time systems. So you might not have an OS at all, or you may have a real-time OS, which is just barely a scheduler and a couple IPC primitives. And so if you have a lot of data, you don't want to run through compressing or decompressing that all in one blocking step, because at that point, either the car has exploded or the USB bus has decided that you're not actually connected anymore because you're not responding to the keep alive packet once every millisecond or that sort of thing. Or if you're like parsing radio data as it's streaming in, you'll completely fall out of sync with it. So I looked around for options for data compression that would actually work in an embedded system and came up empty-handed. There were a couple, decompression in particular, that were available, but some of them had bad licenses. Some of them used more space than I actually was able to use. Most of them worked in one pass. And I didn't really see anything that did compression on an embedded system, which is important because you often have like very repetitive sensor data that you're reading periodically, and you mostly care about when it changes, but you want to record everything that you can and then do processing on it later. And if you can collapse a lot of very similar data together, You can do a lot more with the tiny, tiny bit of space that you have. So I made an implementation of LZSS, which I called heatshrink, which is the sliding window technique. And this is designed so that it scales way, way, way down, and it can do real useful data decompression in under 50 bytes of memory. And if you want to do compression on the embedded system, it takes about 100 bytes. If you have more memory than that, it can take advantage of it and compress more effectively. But that's the bare minimum to get something useful out of it. And most systems can at least manage that. And it doesn't take a whole lot of ROM space either. The code is usually under a kilobyte when it's compiled. And that's under a BSD style license. I actually had to find a particular BSD variant license that didn't have weird considerations for when stuff was distributed only as hardware, which is something that I hadn't really thought of evaluating licenses, but turns out to be really important. So the way that I implement, oh, and I chose LZSS because the output buffer is also the working set for the decompression patterns, which means that it can get by with a much smaller amount of space than other things that need temporary data structures for like a Huffman tree or something like that while they're working. So the way that I implemented this was by creating a big formal state machine for it, where I was able to represent all of the transitions and ensure that if I had to suspend and resume on individual bits of I/O, because this is being coroutine with other stuff that's going on, then I could be sure to keep the information that I needed and then be able to restore that later on to continue where I left off. And so the API for this, my favorite way of describing it is something where you dump in data and then you turn the crank and then you just keep turning the crank until nothing more comes out. And then you dump in more data and keep turning and so on and so on. And once you're done, you tell it that you aren't going to have any more input and then keep turning the crank until you reach the end of the output stream and then tear the whole thing down. And modeling this as a state machine helped shake out a lot of edge cases. So the blue transitions here are where the user of the library is inputting data into it. And the red transitions are where it is sending output into an output buffer that the user has supplied. And then there are also many states that actually have red and blue arcs on them. And that way, if it's expanding a very, very large pattern, it can expand it step by step, even if there's a very small buffer that's going into. It'll fill it up, say that it's done, you copy that somewhere else or do whatever with it, and then after that, you call it again, and then it fills up the buffer again, and you just incrementally step through all of the output. And also, by controlling the size of these buffers, you can also configure how much work it does in a single step. So if you have very, very hard real-time guarantees and you have to do all of your processing in, say, 200 microseconds or something per step, that's an option. And I chose the decompression state machine for this because most of the complexity is in the compression, and that will not fit on one slide. But the other thing I like about this diagram is that it actually has a bug in it. And it's the first thing that jumps out at me now, but when I originally made the library, the size of the offset into the sliding window was always 8 bits or less. So that was 1 byte that I could buffer inside the data structure for it, accumulate the bits for it, and then when it was done, move on. And just before I released the library, I increased that because sometimes it's useful to have, say, a 4 kilobyte buffer or something, and that's what, 12 bits? So that way, you might be reading like a length counter out of the bit stream, but then that means that there's actually more than 1 byte involved there. And I didn't want to increase the size of the accumulator because of some alignment issues and stuff, and it would have wound up taking a lot more space, all just like ugly C details. But so what I had to do was take this state here, where if it was accumulating 12 bits from the input stream, and it got 5 of them, and then suspended and then resumed, it would throw those away. It wouldn't retain them properly. So I had to take that step and split it in half to getting the upper couple bits if the size was defined to be that large, and then accumulate the lower bits. And then that worked fine. So here's a demo of heatshrink running on a big block of text. This is a software license agreement. And like all software license agreements, it says that you should not use it to design, manufacture, or produce nuclear, missiles, chemical, or biological weapons. Any of you want to guess what this is the license for? I'm sorry? Yeah, iTunes. Good guess. So I passed this through heatshrink, and it goes from that to that. And each one of those pound signs there is 11 bits rather than an 8-bit character. This is assuming an ASCII encoding for that. And I specifically chose a software license because if you look at some of the patterns that it picks up on, it's very clear that this is in legalese. This can be like a nice way of fingerprinting a document and seeing what the significant phrases are in it, even if you don't actually care about reducing the size of it, and that's a pretty cheap operation. So it noticed that the big cumbersome phrase, the licensed application, if it could represent that in a couple bits, there was a really major size savings. And likewise, United States law, without limitation, the, and may not be. And in the case of without limitation, the, it's dropping the leading W, I assume, because sometimes it's uppercase, sometimes it's lowercase. But it also picked up on some kind of counterintuitive substitutions like chun, ational, and edin any. But when LZSS has a really, really big buffer to dip into, it can just pick up on a lot of stuff like that. So also there's lossy compression, which is a lot more data specific. Lossless compression has to work in the general case, but lossy compression assumes that you're working with a certain kind of image data or audio data or something like that. And it's really a kind of smart degradation of that content where it can throw away details that the human eye might not pick up on or most people won't be able to hear. And there's like a slider there for if you don't mind if the quality of it starts to get low, but you need it to be really, really small, you can start cutting a little deeper. And so I have an example here where I have this image 3 times. On the left, there's the original image. In the middle, I've decreased the quality of it, so it's actually half the file size. It goes from 51K to 27K. But you can't really tell a difference unless you look at it really close. And some details, like the edges or the reflections in the glass or the shadows or the wood grain, tend to show that more. But then I have the size of that one more time, and it goes from 27 to 14K, and then that gets really pixely. Because the way that JPEG compression works, the primary way that it works is breaking an image into an 8x8 pixel grid and getting the average color, and then applying a bunch of, a certain number of gradients over that then add other details onto it, and they're translucent, and the way that those overlap ends up defining most of the detail in the image. So in closing, I've talked about why data compression matters, how to design data so that it can be compressed more effectively, talked about lossless compression algorithms, and then there's the case study of heatshrink and the example of lossy compression. So if you want to learn more about this, here are 2 books that I particularly like, Managing Gigabytes and Information Theory, Inference, and Learning Algorithms, the latter of which also has a bunch of machine learning and some other topics in it, and there's certainly overlap there. And there's a free PDF of that on the author's site if you're interested. And also, I work for a really cool, transparent company in Michigan, and if you know anyone who wants to do cool work for a small company, we're hiring at our Detroit and Ann Arbor offices. So I have a couple minutes for questions, I think. Anybody? Yes?
So this isn't so much a question, but if you're using one of the dictionary compression algorithms, if your application, like the data that you're using for your application was regular, you can actually pre-compute the dictionary and then store it in commands, so like ship it to your application or download it and then save all of the space in the dictionary. So you have like a giant dictionary, like a very efficient compression. Because you only understand it once, you can reuse it. And actually, if you're using the gzip, the API lets you do that. So you can actually have the dictionary, have a data structure that represents your dictionary, and pass it in as a pointer to the decompression thing.
Okay, to try to summarize that for the people who can't hear you, he said that if you're doing compression on a known data type, you can pre-compute what a good table of substitutions would be, and then build that into your application and not need to represent that explicitly in the data stream. And that's a case where you know a lot more about your problem domain than just a very, very general compression algorithm. And there's a certain point where that turns into designing a binary coding for your data format by hand. But it's good to know that tools like zlib can also automate a lot of that work. Anybody else? In the back?
What is the algorithm that XD is based on?
That what?
XD?
I don't know. Okay. Yeah, and I couldn't fit LZMA into this talk. I kind of typed for time as is. So yeah, there's a bunch of other algorithms. I mostly focused on those particular ones because they're the ones that I'm most familiar with, but I was also looking at ones that tended to scale down rather than up. There's some interesting stuff that Google and a couple other really large companies are adding to their infrastructure that make very different trade-offs for, like, if you have a lot of memory and want maximal efficiency of the compression. That's kind of the opposite of the problem that I have, so I didn't really go into that. Anybody else? Yes? Well, the question was, how do you weigh the benefits of these different algorithms against each other and decide what's most suitable for your application? You could, if you have a really solid intuition about how they work, you can think about how that might impact your data, but really the easiest thing to do is just to find what you consider representative data and then do a bunch of experiments and benchmarking and see. And then maybe reevaluate that on a periodic basis if the character of your data starts to change. But it's easiest to just run it and measure. It's not something that you need really elaborate infrastructure for. Anybody else? Yes?
Can you talk about any schemes for indexing to compress data?
That's another talk. That would be a talk that I would love to attend, but that's another talk. Okay. Anybody else? Yes?
Are you working on any other compression libraries for that?
Not at the moment. I would love to talk with you afterward, though, if you're interested in that space. So, okay. Anybody else? Oh, the book slide? Sure. And like I said, the one on the right there, there's a free PDF of it on the author's site. And the one on the left is not free, but well worth it. So, okay, one final question, because it looks like I'm getting out of time. Okay, thanks.